the last module, we ended with a definition and a proposition regarding absolute and conditional convergence. Let me just recall the definition because it's going to be the central aspect of this particular lecture. Definition: suppose AN is a sequence such that summation mod AN converges, then we say summation AN converges absolutely. Not a very creative name, but nevertheless it serves the purpose. If summation AN converges but summation mod AN does not, then summation AN is said to be conditionally convergent. Conditionally convergent. We also stated a proposition. If summation AN converges absolutely, then summation AN converges. Okay, let's see a proof of this. It is actually done already, but since this is the central portion of this, I'll give a quick proof, leaving the details to you. Okay, since summation mod AN converges, that's the hypothesis, for epsilon greater than 0, we can find n epsilon such that if n is greater than m is greater than n epsilon, then summation j equals m to n mod aj is less than epsilon. This is just the Cauchy criterion, one side of the Cauchy criterion. Remember, Cauchy criterion is an if and only if condition. But summation j equals m to n aj modulus is less than summation j equal to m to n mod aj is less than epsilon. This is just triangle inequality. So again, by the other direction of Cauchy criterion, by Cauchy criterion, summation mod an converges. So this was a fairly straightforward and easy proof. Now we are going to be studying series now that converge but conditionally, not absolutely. And the study of such series is really interesting. That is best seen by studying an actual example. Let's take the example of the alternating harmonic series. This is the sum 1 minus half plus 1 by 3 minus 1 by 4 plus 1 by 5 minus 1 by 6 and so on. Okay. Now actually it's better if I write a few more terms. You will understand why in a moment. Let me just move this little bit to the side so that I can write a few more terms. I missed a 6. Minus 1 by 6 plus 1 by 7 minus 1 by 8 plus 1 by 9 minus 1 by 10 plus dot dot dot. Okay. This is the alternating harmonic series. It's just the series summation 1 by n where I have inserted minuses at every other place. Okay. Now we know that this series is not absolutely convergent because the harmonic series diverges. This series is not absolutely convergent. Okay. Now let us for the time being assume that this converges to some L. This is equal to some L, let's say. I am not going to compute L now, nor am I going to show that this series in fact converges to something at all right now. We will see it in a more general theorem, because proving that this series converges is the same as proving a much more general fact. There is no additional difficulty. I will do that in a moment. That's the alternating series test. But let's just assume for the time being that this converges to L. Bear with me for a few minutes. Okay. Now what I'm going to do is I'm going to explore a question that I had raised all the way back in the beginning about whether you can manipulate infinite series with the same level of freedom with which you can manipulate finite series. You can rearrange the terms of a finite series, you can group terms together, and so on. All the familiar laws of arithmetic hold. But what about infinite series manipulation? Let's see what happens if we manipulate this series. What I'm going to do is the following. I'm going to rewrite this as 1 minus half plus 1 by 3. No, that's not the way I'm going to do it. I'm not change anything at all. What I'll do is I'll move this minus 1 by 4 here, then put 1 by 3 here. Okay. So all I have done is I have grouped together two negative terms. Then what I'm going to do is I'm going to group the next two negative terms, 1 minus 6 and 1 minus 8. Then the positive term is going to come. Okay. Then I'm going to group the next two negative terms, which I'm not mistaken is minus 1 by 10 and minus 1 by 12, and the next positive term is 1 by 7 plus dot dot dot. Okay. Note very carefully that every term in the original series will occur here, but in a different position, because instead of alternating one positive and one negative, I am taking one positive, two negative, one positive, two negative, one positive, two negative, so on. So what I will do now is I am going to group these terms together after doing this rearrangement. I am going to write it as 1 minus half minus 1 by 4 plus 1 by 3 minus 1 by 6 minus 1 by 8 plus 1 by 5 minus 1 by 10 minus 1 by 12, and you get the picture what is happening. Okay. Now this is just half minus 1 by 4 plus 1 by 6 minus 1 by 8 plus 1 by 10 minus 1 by 12, so on. You can just see that this is what will happen if you do this manipulation. Please check this rigorously. I'm being a bit hand wavy because there's nothing really deep happening. This is just basic arithmetic. Okay, wonderful. Now this is just half into 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 minus 1 by 6 and so on. Lo and behold, this is the original series. Okay. So if this original series were to converge to L, then this rearrangement where I have just bunched together terms in a different way, this should converge to half L. So something interesting is happening. If you rearrange the terms of this series, which is not absolutely convergent, but it is actually convergent, which we are going to see now, then if you rearrange, you get a different value for the sum. In fact, you get half of the original value. Now I leave it to you to check what will happen if I group these terms differently. Instead of 1 positive and 2 negative, what if you do 1 positive, 3 negative, 2 positive, 5 negative? Okay. If you're not able to make headway, please Google search rearranging the alternating series. I'll give you a link below and just see the various results that have been done. What and all can you get by rearranging this? Okay. In the next module, I will prove a very abstract theorem, or rather sketch the proof of a very abstract theorem saying that you can rearrange and get anything. That's a precise statement called the Riemann's rearrangement theorem. You can get anything by just rearranging the terms here. Okay. So, but I am talking about specific rearrangements in this module where some positive terms are grouped together, then negative terms are grouped together. That is, it's a fixed pattern and you will get some interesting stuff. Okay. So now it is interesting to see whether this alternating series actually converges, this alternating harmonic series. That's the content of the next theorem, which is also called the alternating series test, or Leibniz test. This is as follows. Suppose an is a decreasing sequence of positive reals and an converges to 0. Then summation minus 1 power n plus 1 an converges. If you have a series of alternating terms such that after you throw away the sign, if you consider the sequence an and that sequence an goes to 0, moreover it is all going to be greater than or equal to 0 and decreasing, then the series converges. Minus 1 power n plus 1 an converges. Before I give the proof, I want you to solve this exercise. Solve it right now in your head. You need not write down a proof instantly, but just solve it right now in the end, right now in your head. Suppose an is a sequence and suppose, let me just change it slightly. Suppose summation an is a series such that the odd partial sums Sm, or rather S2m, I am just taking the partial sums of even number of terms collected together, and so this is 2m plus 1, and even partial sums S2m both converge to L. Then summation an equals L. Suppose I am giving you a series such that I know that if I collect together even number of terms, that means the first sum of the first 2 terms, the sum of the first 4 terms, the sum of the first 6, 8, 10, 12, so on, that sequence converges to L. Then I consider the first 3, the first 5, the first 7, so on. That's the odd partial sums. If that also converges to L, then the whole series converges to L. This is a rather straightforward exercise that falls out on your lap immediately from the very definition of convergence. Now let's prove the theorem. Let's give the proof of the theorem. I am going to assume this exercise. That's why I want you to solve this exercise immediately in your head at least, if not on pencil and paper. Okay. Now aim is to analyze S2m and S2m plus 1. Okay. Let's just analyze S2m first. Okay. So what is the S2m going to be? It's going to be, first term is a1 minus a2, then a1 minus a2 plus a3 minus a4, and so on. Okay. Now observe the following. This a1 minus a2 is certainly going to be less than or equal to a1. Right? Now when you are adding back a3 in absolute value is certainly less than a2, right? So I have subtracted a2 but added back something of value less than a2, then I am subtracting a4 again. Whatever happens, this is also going to be less than or equal to a1. Okay? And if you observe carefully, at every point of time when I am adding 2 terms, the magnitude of those 2 terms will always be a positive quantity, because for instance here I am adding a3 minus a4. Okay, I am always going to be adding a positive quantity, but that positive quantity cannot offset the negativity coming from the previous quantity. Okay, so at each stage I will always get less than or equal to A1. Moreover, it's an increasing sequence. Both should be very patently clear from what I have said. So S2m is an increasing sequence bounded above by A1. Okay. So by monotone convergence theorem, S2m converges to some L1. Okay. Now let's look at S2m plus 1. So the first term will be A1, then it will be A1 minus A2 plus A3, then A1 minus A2 plus A3 minus A4 plus A5. Okay. So these are the first few terms. Now observe that these are all going to be greater than or equal to 0. Let's see why that is the case. Now A1 is certainly greater than or equal to 0 simply because A1 is a positive quantity. Now I am subtracting a quantity A2 whose magnitude is less than A1. So I am left with a positive quantity. Then I am adding back another positive quantity A3. So this will be greater than or equal to 0. In a similar way, you can see that all these terms will be greater than or equal to 0. I will always be subtracting a quantity and then adding back. So in any case, it will always be a positive quantity. Moreover, look at what is happening. I have subtracted A2 from A1 and added back a quantity whose magnitude is less than A2 because A3 is less than or equal to A2. Similarly, in this, I have subtracted A4 but added back a quantity whose magnitude is lesser. So S2m plus 1 is a decreasing sequence bounded below by 0. Okay. So S2m plus 1 converges to some L2. Okay. Now notice that if I consider limit m going to infinity S2m plus 1 minus S2m, I am left with limit m going to infinity of A2m plus 1 which goes to 0, right? Which goes to 0. Why does A2m plus 1 go to 0? Because that's in their hypothesis that the sequence AM converges to 0. So A2m plus 1 will also converge to 0. What does this tell us? This tells us that limit of m going to infinity S2m minus 2m plus 1 minus 2m, which is nothing but L1 minus L2, this is 0. Or in other words, L1 equal to L2. Now by exercise we are done. Okay. So we have now shown that if you have an alternating series with the terms of the sequence going to 0 and decreasing and positive, then the alternating series converges. Okay. So this concludes this module. In the next module, we will see the famous Riemann's rearrangement theorem and also see that if you have an absolutely convergent series, then you can rearrange without this fear. This is a course on real analysis and you have just watched a module on absolute convergence and conditional convergence.